Hi, good afternoon, everybody. Thank you for joining us today. Today we're going to be going over why we feel here at WB Engineering that technology is essential to succeed, particularly in our space. We are a product design and development firm, and we also are partners with 3D Systems. In order for us to be able to compete with larger firms, we have to invest heavily in technology. So what we're going to do is just walk through how we leverage technology, not just 3D printing. We're going to take a little bit more of a global view today as to how technology in general helps us get the edge over our competition when it comes to design work, and then also how we help our customers lean out their process via technology, and how maybe some of these things can be applicable in your workspace. So what's going to be on the menu today? Let me go ahead and okay, so today for why technology is an intricate part of a product design cycle, what we're going to be doing is going over first, who's WB Engineering. Then we're going to be focusing quite a bit on a case study. It's a product that we developed here internally, pharmaceutical product, and we'll show you how we actually used not only 3D printing but 3D scanning and CAD software in order to refine our design efficiently and in a very tight time period. Next, we're going to be going into the technology that we used, specifically simulation and 3D printing, scanning, and then we're going to go into a brief of what the technologies are. Okay, so who's WB Engineering? So WB Engineering is a product development company, like I just mentioned. We focus on medical devices, consumer products, aerospace in terms of product design and development. We're also a 3D Systems partner. We sell and support 3D Systems printers for the state of Florida. And then also we are a consulting partner for a lot of companies where we will be brought in to help with the product development process, or where they're outsourced for manufacturing, and we can also help optimize designs. So we're a high-tech boutique product development firm. We actually compete quite a bit with big boys out in Silicon Valley, and we win. The reason why we're able to is because we can actually leverage CAD software, 3D scanning, and 3D printing, which helps us compress our design cycles quite a bit, increase margins for our customers, and we can create physical prototypes and digital prototypes with ease using software. Now, the case study we're going to be going over today is CleverCap. They have a website, clevercap.org. You can visit them as well to find out more about the product on your end. But essentially, what is a CleverCap? A CleverCap is a medical compliance pharmaceutical device. Therefore, it's a high-tech pill dispenser, let's call it. What it does is it monitors the dosing of pills and reports back to your caretaker, doctor, whoever it might be. Now, what's the significance and why we bring this up? Well, there was a lot of different tasks that were thrown on our table. Initially, the product was far more simplistic until the customer experienced a significant amount of scope creep. So that is a bad thing all around, right? What you originally anticipated now turns into a large project. So what did we have to do? We had to design a passive mechanical sorting device with the ability to adapt to a wide range of pharmaceutical pills without expensive electronics and limiting the mechanical complexity in order to have this in a handheld device and also reach a target price point, right? So in order to do something like that, we had to actually have a closed loop system. So if the user dispensed one pill, we had to make sure we counted that one pill. Not to mention, we had to make sure that we accounted for all different types of pills, different sizes of pills, and made sure that we can control that to a very high % of success rate to ensure that what we're reporting back to the caretakers is exactly what happened. So what technology did we use to develop this product, right? So we actually used Autodesk Inventor Professional. We used Autodesk Mechanical Simulation, Autodesk Inventor Mold Flow, Autodesk 3ds Max for some renders. On the 3D printing side, we use 3D Systems ProJet 3600, HD Max, and we also even used for for the emergency release, which I'll show you, which is kind of a polypropylene part. We used one of a higher-end SLA printers for the mechanical properties of the parts, and then to verify the manufacturing quality, we use Capture 3D Scanner and Verify software. So let me go ahead and ask you guys a couple questions here. I want to make sure that we kind of cater this to the crowd. So what we want to do is find out, do you currently use CAD in your design process? Okay, looks like everybody answered very quickly. Looks like 100% of us use CAD, which is great. That's good. That's good to know. I'm glad that we're on the same page there. Now I'm going to ask a quick follow-up. So, do you currently use 3D printing as part of your design cycle? Okay, a couple more seconds so everybody gets in. All right, sounds good. So it looks like the vast majority of the people attending today do not currently use 3D printing. So hopefully after we go over this today, you'll see some value in 3D printing and why at least we feel it's actually absolutely necessary in order to at least make us successful, right? You always have to look at these presentations with an asterisk on them, right? Because everybody's industry is different, everybody's application is different. So I don't want to mislead anybody into thinking that 3D printing is a one size fits all. Because by no means are we there yet. So what challenges were we facing, or what challenges was the customer facing when we got this project? So one was marketing samples were required for initial and early funding, right? So we had to produce something physical for the customer to take out and show off to customers prior to investing quite a bit of money, and not to mention time into injection molds and the manufacturing process. The customer had extremely tight timelines. Customer also experienced quite a bit of scope creep. He understood via his market research one thing, and then once he started getting a little bit further into it and actually started reaching the customers that he wanted to get to, it was a far more complex product that he had to develop. He also, again, limited startup costs, so he had prototyping costs that he had to worry about. We also had to pass child safety testing prior to getting the final round of funding, FDA approvals, and also limiting the manufacturing costs. So at this point, what do we do? So to start off the product design cycle, we design our product. Everybody here on this webinar uses CAD, so we won't focus too much on how we actually design CAD stuff, but what we focus on quite a bit is actually validating our designs digitally, right? So being that we're a relatively small company, we need to superpower our engineers here. So how do we do that? We actually run all of our designs through a wide range of different types of simulations using our simulation software here. So as we all probably know, things when they break, they don't necessarily break the first time around, they break the nth time, right? So you might want to do some cyclic testing on it. You also want to make sure you do some FEA analysis on it, so you do some finite element analysis, check for stress testing, dynamic simulation as well to find out how these parts interact with each other, right? Because you might have one part assembled with another, but as soon as you start moving things around, there could be some collisions that you need to detect. Then once you have your part designed, you need to start focusing also on simulating the manufacturing process, right? Can you make this lighter? Can you reduce the amount of weight that's in here? Once you injection mold it, if it's a plastic part, will it have defects when it comes off? And also, can you optimize the cycle time and compress that cycle time so that you're not wasting all of your time on a slow fill or a part that's hard to fill or a long cooling cycle, what have you. You also have to pay attention to other simulations like temperatures, drop test, if it's something with fluids, how does that affect the fluid even when you have different temperature environments, etc. So this is just an example of one of the ways that we'll actually, verify things using dynamic simulation. So this is actually a look into the pill sorter itself. This is our dynamic simulation of how these pills were actually going to be routed down this helical kind of funnel design that we came up with. Now, we did that not once, not twice, but quite a bit of times. In our design cycle, because we needed to make sure that when we did go to 3D printing, that we did have it within a high percentage of success rate, right? So we ran those dynamic simulations, and then we went on to actually making some physical prototypes. So I'll make a quick pause right here again. I want to see if we can get a couple more answers from you guys. So, what kind of simulations do you currently, what kind of simulations do you currently use during your product design process? Do you actually do any FEA analysis? Do you do any dynamic simulation or CFD for your analysis? Also, are there any fatigue tests that you do digitally to ensure that this is something that's going to be working? Okay, I'm still waiting on some people to answer. I'll give you guys a couple more seconds to see if we can get some answers from you guys, and we'll move on to the next one. Okay, so a couple more stragglers, see if we can get them in. Okay, so it doesn't look like very many people use the finite element analysis here. So what we're going to be doing is just moving forward, and we'll, if you need any type of information on FEA analysis, dynamic simulations, we can help you out with that. Okay, next. So 3D printing. So how did this help us in our Clever Cap design, right? So our customer had a lot of challenges, right? Primarily at the beginning was funding. Then it quickly transformed into time. Both of those play very well to the 3D printing process. Now, this product is perfect for 3D printing. Why? Because it's small, complex, injection molded plastic parts, right? Now, I want to also say that try to be a little bit creative when you think about 3D printing. A lot of the times we develop and design things in-house that aren't necessarily going to be plastic at the end of the day. But we use 3D printing to verify fit, maybe not function, but we make sure that maybe the 3D printed part is sized correctly, is designed correctly, or if it's ergonomics, fits in the person's hand. The other thing is you can use 3D printing as an intermediary. So don't necessarily think about the 3D printed part as the end product. Maybe you need it as a jig or fixture to help you machine your metal part more efficiently or more quickly. Or maybe during the assembly process. The assembly process maybe requires a complex pattern of holding things in certain positions in order to make some alignments. So think of it as something that can help you rapidly generate complex tools to assist you in either the assembly design or manufacturing of your product. So in our scenario, what we used after we leveraged CAD software in order to make sure our design was intact, we used 3D printing to simultaneously and inexpensively make benchmark products in order to test with our customers. So just a scenario, we would have a design meeting in the morning. We'd suggest a couple different designs that we wanted to try out. Our engineers would work throughout the day, maybe the next 2 days, to update their designs. And then we would submit them all simultaneously to our 3D printers. What does that do? That means the next day we actually have all of our parts finished and ready for testing. So we didn't have to make decisions solely based off of a digital model or due to time constraints or budget constraints. With the 3D printer, we were able to try out the variety of options that we were looking into, and we were able to test them simultaneously without adding more time to the timeline and also adding cost to the customer, right? So in the image on the right, this is actually right off of the 3D printer. It's a full CleverCap assembly. That's how it comes off of the print, and then you just have to take it from there, put it inside of an oven to take off the wax, and you're good to go. On the left is actually short-run manufacturing that we did on our 3D printer, where we actually 3D printed 500 different what we call inserts, which are the things that actually receive the pill at the end of the device. So it's actually what is the modifiable or custom part that is specific to, let's just say, a Pfizer pill or a Merck pill. So what we had to do was account for a wide range of different pills and have them tested beforehand before going into injection molding and manufacturing in a very tight timeline. So we actually did use 3D printing for short-run manufacturing. Not to mention, we also used a 3D printer to get us our initial samples for child safety testing. So we were actually able to add the electronics to this device, make sure everything fit correctly. Then we actually took that same model and we gave it to a facility, a third-party facility, to actually run child safety testing on a 3D printed model in order to get that out of the way, and then that allowed our customer to actually go for another round of funding because now he has a child safe approved product, and it adds more validity to his design before he actually has to spend the money and the time to wait on his molds. So this is actually the evolution of our CleverCap, right? So this is kind of showing how it evolved throughout the process and how we use 3D printing in the evolution of the CleverCap. So on the far left, this is what we would call FDM, so it's fused deposition modeling. It's very low resolution 3D printing. That would be off of 3D Systems Cube Pro printer. This printer, and I'll get into the details of the printers in a little bit, but this printer is good for quick and dirty prototypes, something that you just need in a few hours. It's not something that you're going to try to do or check high resolution or tight tolerance assemblies with. It's just something to kind of check if you're in the ballpark. As you start moving over to the right, all the ones to the right are what we call multi-jet printing models, so MJP models off of our ProJet 3600. These are the ones that we actually use during the child safe testing, during functional testing, also optimizing the assembly process. We use it for jigs and fixtures, etc. Now, when you get to the fourth model from the left, that's actually a 3D printed model that we then painted and put a silkscreen logo on it. That was what was used to get marketing, or he was using for marketing to go get more investors involved. And also, that's the same version we use for child safety testing. So if you count from left to right, number 4 and 5, those are 3D printed versions of it that we use not only for functional testing, but also for the child safety. Now, the last two on the far right, those are actually production and use product injection molded parts, right? So if you notice, there's a slight difference between the two in the middle to the ones on the right, but the injection molded one is almost a one-to-one copy to what we had 3D printed, and therefore the customer was able to enjoy the benefits of having basically a final product without investing upwards of 6 figures in tooling in order to get his production started. Okay, so next poll. So this question is, how do you guys verify your designs before you actually go into manufacturing? Do you use digital simulations like the FEA analysis, dynamic simulations, cyclic testing, things like that? Do you use 3D printing? Do you actually use prototype molds, CNC machines, things like that? So the reason why we ask this is because we want to understand, how currently people are taking care of these tasks, and what kind of obstacles you guys might be coming across. Looks like everybody answered that one. Let me go ahead and close that one out. Okay, so once we found that we had our design finalized and we felt like it was ready to go to manufacturing, we got child safe approval off of the 3D print, etc., we then went into mold analysis, right? So we actually used Autodesk Mold Flow Advisor for this. This is one of the tools we use in-house that helps us out significantly because before our customer is going to invest tens of thousands of dollars, and also minimum 4 to 5 weeks or 6 weeks or even in some cases 12 weeks to wait for their mold, we want to make sure that we're telling them to go to manufacturing with something that's actually going to work. So we actually go through the process of actually checking the flow. So we'll actually optimize the part specifically for the plastic that's being used and be able to configure the part to have the gates in the positions that are not going to affect tolerance critical parts. Not to mention, we want to make sure that we check for warpage, things like that. So this is just a real quick GIF of the flow of the plastic. This next one is actually fill time analysis, right? So one of the biggest costs that you're going to have with injection molded plastic specifically, besides the actual material cost, is the time that it actually takes to injection mold this. So we've actually worked with companies, large companies that make products by the hundreds of millions per year, and we've actually been employed to help them optimize the design so that they can actually fill their part faster without impeding quality. If you can imagine, you shave 25% off of the fill time, you're actually starting to get a significant amount of savings over the course of hundreds of millions of units. This is another example of how we use 3D printing with the simulation software. So from left to right, you'll notice on the left we have a 3D printed part. This is directly off of our 3D printer. And forgive me, the example is a little bit hard to follow, but I'll try to be as descriptive as possible. But the model on the left is as designed by CAD, right? So we designed this part in CAD. It looks perfect. It's perfectly symmetrical on our screen. When we 3D print it, if you have a very high resolution 3D printer, it should come off perfect within a couple thousandths of an inch. When you get it off the other side, everything should be fine. Now, when you go to injection molding, that's the thermal process. Things start to change, right? So what did we do? We did the simulation for the injection molding. This is just an example, right? We intentionally designed this to have some warpage to fail so that we can actually show this as an example. But the one in the middle is actually off of one of our CJP printers, our color jet printers, where we actually superimposed the bitmap from the simulation on it. So where you see the discoloration, that's actually where the part actually starts to warp when it comes out of the injection molding process. So if we simulated this, for example, in ABS, we run the simulation with ABS, then we 3D print the part as deformed with the bitmap on it, and then we see if that's an acceptable range of deformation. The one on the far right, that's the one that's a little bit hard to tell, but that's actually us 3D printing the warped version of the model, right? So on the left, true to CAD. On the right, basically one-to-one with how it's going to come off of the manufacturing floor. So this is what we found to be extremely useful as well for 3D printing, because though you might think you have your product completely designed, there's differences in the manufacturing processes, and you want to make sure you take that into consideration before you start cutting steel as well. The next thing is 3D scanning, right? We use 3D scanning to help us out significantly here, right? We're a small company, and sometimes when things don't go right, everybody starts pointing fingers, and we just want to make sure that we have our bases covered on our end, right? So we submit a certain design, we've done the 3D printing, we've done the simulations, we've even 3D printed the warped parts to make sure that the warpage isn't going to be causing an issue. Now we get our samples back from the manufacturer. Well, we need to make sure that we verify those, right? So how do we do that? We actually use a blue light 3D scanner from 3D Systems called the Geomagic Capture. That gets literally millions and millions of points from one scan, as opposed to using either a caliper or CMM device that might take a very long time. With this particular device, we have some radiuses on here. We have some parts that are very hard to caliper. So with a 3D scanner, it just makes perfect sense to do it this way. We're able to inspect with millions of points the entire device in less than an hour, as opposed to spending several days on this. So when we go into here, this is the kind of things that we'll actually look at. So this is actually a scan of the top section of the Clever Cap. So you'll see the nominal CAD on the left, the scan data in the middle, and then you'll see one sectional view right there on the right, which actually shows there was a change that was implemented in the mold that we had requested, which we might have had some issues finding before. And you notice some red areas around the circular part on the bottom that actually has sync that gets into about a millimeter range. So that could or could not be acceptable based off of your manufacturing process. The reason why I say this isn't so much so that you can start pointing the finger as to who's wrong or who's right, but it helps you diagnose why things aren't working perfectly, right? So if you have a very clear picture of what's off from your nominal design, what is off from your 3D printed version, then you have a very good tool to now start troubleshooting and working with the manufacturer hand to hand to make sure that, okay, these issues get addressed and you find out why this is not working in a timely fashion. Furthermore, we can actually do things like animations, right? So I'm not saying that everybody on this webinar is even interested in this kind of stuff, but it helps, right? If you have an idea that you're trying to convey to the rest of your team or to management or to potential investors, it's nice to be able to illustrate this without having to go through the manufacturing process or even 3D printing process, right? So you can actually make one of these animations using some of your CAD software relatively easy. So we don't actually represent any type of CAD software, but I do recommend that you guys do look at a full suite of software from, whether it be Autodesk, which was what we use, or SolidWorks, because it is something that we leverage heavily here in-house, and it helps us actually minimize the amount of prototypes that we actually create. So specifically, if you're using traditional methodologies of manufacturing that could, tack on a lead time of a couple weeks because the machine shop's backed up, or even just the cost in general, right? Everybody running those machines, they don't work for free. They have a certain cost associated to them, and there's also priorities that have to be respected as well. So, your product could be pushed back quite a bit simply because you don't have anything to show for it. Okay, so let's go ahead and add another poll here. Okay, so now let's see, how many prototypes do you currently make while you're designing and developing a product? I'll tell you on our end, we actually make a significant amount. We're in that 4+ range. Not because we like making prototypes, it's because we like trying to optimize our designs as much as possible. So I'll wait a little bit while everybody kind of fills in the questionnaire. Might be doing some counting out there, and then I'll move forward. So we still have a couple more people that need to vote. We're almost there. All right, I'll wait for, I think we only have 1 or 2 more people left. See if they, maybe they're taking a sip of their coffee. Okay, let me go ahead and close this one out. Okay, one more question. So how do you currently check and validate the parts that are already in manufacturing? Do you currently use CMM, calipers, go, no-go gauges? Do you do visual inspections? Do you use 3D scanning? Okay, we have the majority of the people answered so far. I'll give a couple more seconds to the last couple people. All right, go ahead and close this one out. So technology review. So let's talk about the technology that we actually use in a little bit more detail. We're going to kind of skip over the software. What we're saying is essentially, make sure you're using not only a CAD software, but you're also using simulation software. That's where you get the most bang for your buck. We use Autodesk in-house, but I know SolidWorks and Dassault, they offer great packages as well. But the long story short is leverage technology to get your design right quickly and right off the bat. If we didn't use that, we probably would have failed as a company years ago. So that's one of the key factors to our success is really leveraging a full suite of software, not only 3D CAD, but also the simulation behind it. Now, 3D printing and 3D scanning, we'll get a little bit more into detail there, and specifically on the 3D printers that we use for this actual project. So we use technology called MJP, which is multi-jet printing. So why did we use MJP? Well, it has a very wide range of applications. I mean, we have this printer in-house. We chose it because of its versatility and because of its precision. It is capital equipment, right? So it's not something that everybody can just up and buy on a whim's notice. These printers do start around the 50K range, so it's capital expenses. But what do we use this for? We use it for everything from conceptual designs to engineering and validation verification, pre-production samples, functional prototypes like we used in the Clever Cap, where we actually did that for child safety testing. You can actually 3D print molds off of this. They do offer a high temp material via 3D systems that can be used for injection molding, which helps out quite a bit. Then we also have a we use it for communication purposes as well, as our customer took that model out and showed it to potential investors as a sample to trade shows, etc. In addition to that, they actually had the prototype win them an award as well. So they actually ended up winning an award just off of the prototype itself. This printer does offer very high tolerances and accuracy, right? So you can get things that can help you, check the tolerance and accuracy of an injection molded part right off of this 3D printer. So that's one of the things I want to focus on just a tad bit is, you have to be careful what 3D printer you go with, because you don't want to end up with a false positive or a false negative. We've seen scenarios where our customers, because we do offer just manufacturing as a service as well, and our customers go off of a 3D printed model. They say, yeah, it works perfect. They get the injection molded part, and it actually doesn't work out. The reason being is because the 3D printed version was actually warped. So always make sure that you're using a 3D printer that has the resolution and tolerance that you need for your application. If you're trying to injection mold or machine something to plus or minus 0.02 of an inch, make sure your 3D printer can actually handle that kind of tolerance so that you don't get misled by the 3D print. So, make sure that you're getting a 3D printer that it meets what your final production is going to be doing in terms of accuracy. You can also do fit testing, jigs and fixtures. There are some materials on here that are actually class 5 biocompatible, and I think I accidentally put 4 there, so I apologize. You can also use some of the materials for casting, so you can actually investment cast some of these materials. Some of our customers use this for jewelry applications. We have another customer here in Medley that actually uses it to investment cast extremely high precision complex impellers for government contracts. The other one is ergonomics. We have helped customers win large contracts with doctors because they are able to 3D print their model, put it in the doctor's hands, and then the doctor can make the decision via that way as opposed to just looking at something online. It also can do snap fits, and it has a pretty long laundry list of applications. Now, how does multi-jet printing work? Right, so the basics are it uses over 600 jets to eject material. It has multiple material capabilities depending on which one that you actually go with, right? So 3D Systems offers a wide range of multi-jet printers starting from a ProJet 2500, which is a printer that has 5 different materials that it can print in discretely, right? Not multiple materials at the same time, but you can have a rigid material or a flexible material, and you can swap between one and the other. But long story short is you want to look at multi-jet printing for rigid, high precision, high detail plastic parts. Now, if you are in the metal industry, etc., that's fine. You can actually use these parts to cast them, or you can use them as a checkpoint, right? Okay, is this part, when I make it out of metal, going to be accurate, or is it going to work in terms of geometry? Function-wise, limited if you have metal applications. Why? Because obviously the physical properties of the plastic versus the metal are nowhere near each other, so therefore, you have to kind of pick your battles. But if you're looking for high precision without a huge price point like a production SLA offers, multi-jet printing is what you want to look at. I find that for our company and our application, which is we design a large variety of products ranging from metal to injection molded plastic. This seems to be the printer that fits the bill the best because it does have quite a bit of accuracy and versatility in terms of material. So some highlights and benefits of multi-jet printing. It's better than injection molded accuracy, right? So you can hold some very high tolerances with this. You have castable materials, near limitless versions of geometry, right? So I was fortunate enough to start as a design engineer with a 3D printer at my disposal. It was a good and a bad thing. I was under the false assumption that anything that could be 3D printed could be manufactured, which is not true, right? So you are starting to get into the realm of 3D printers doing things that are just impossible to do in terms of traditional manufacturing methodology. So if you do get one of these printers and you do have a novice engineer working on it, please have them learn from my mistakes and make sure that they know what a manufacturable part and what's not, because 3D printing is pushing the limits in terms of geometry, and it doesn't necessarily mean it makes sense for manufacturability and good price point when you try to go to injection molding or whatever process it is that you might be using. So that's just a quick side note there. The limitations is the supports are not reusable on multi-jet printing. Why do I mention that? Well, it's not that inexpensive to print on a 3D printer which uses multi-jet printing. So if you're looking at small, complex geometries that would take a very long time to machine, then this is where you want to look at. If you're doing very large, simplistic geometries, you do not want to look at multi-jet printing. It's going to be an extremely expensive part that is going to take a long time to print as well. So these printers are very high accuracy, but they do take a long time to print in terms of large volume parts, right? So, just to kind of sum it up, very small, intricate plastic parts, perfect. Anything that fits within a cubic foot that's very complex, that's good. But anything bigger than that or simplistic, you might want to look at maybe a different type of printing technology or even your more traditional methodologies like CNC. These are the printers that we offer via 3D Systems, starting from the left with the entry-level Project 2500. We have one of those in the office here. It produces awesome parts, very high resolution. And then you'll see in the middle the two ones that are kind of vertical in shape. Those are the 3600s. Those essentially can produce slightly higher resolution versions of that, and they come in a wax version. And then to the right, we have our 5000 series, which are just larger versions of the other printers. The one on the far right is our 5500, which is actually a multi-material printer, which can print at the same time an elastomeric material or a rigid material. And it actually has digital materials that will allow you to pick any type of durometer between, extremely soft, which I believe the lowest is 30, Shore A30, all the way up to rigid plastic, so you can do Shore A90, no problem on that as well. So overmolded applications, things like that. Now, I did mention that we did use a Pro X800 in our Clever Cap design. Why? Because we needed some mechanical properties that our ProJet 3600 couldn't handle. This we actually outsourced to 3D Systems. Now, we're a reseller for 3D Systems or a partner for 3D Systems, so we can offer that as a service to our customers as well. But long story short is this type of printer can produce polypropylene-like parts, which we didn't have access to in our 3600, so we had to actually use a Pro X800 for that. That was for the part that tears off on the top of the Clever Cap. What's good for SLA? Now, the only reason why you want to look at SLA other than multi-jet printing is if you're doing one, larger parts, parts that have larger volumes with that would be expensive or cost prohibitive to print on a multi-jet printer. The other thing is if you have more end-use type applications, right? We have more variety of medical grade materials. This also has high temp applications, but I'm talking about to a whole nother level than the 3600. We have one customer that does contract manufacturing for the government. They have to do very intricate, fairly large injection molded parts that are almost one-off. They're extremely short run, maybe 10 or so. So what they do is they actually print out the molds in the Pro X800 in a material called bluestone. And they can injection mold it right off of the 3D printed mold. The other thing is they can include conformal cooling, right? So they can actually put cooling channels within the mold to actually speed up the process. So it's very interesting how people are using 3D printing beyond just producing the actual end product. They're using it as intermediaries to the end goal. How does SLA work? Well, let's say, the difference between multi-jet printing and SLA is multi-jet printing actually has to use a wax support, right? So it's a melt-away support, which comes off of the part and leaves no scars, no blemishes, but unfortunately none of that can be recycled back into the machine, so therefore your cost goes up a slight bit. With SLA, all of the support material is actually liquid. It's neutrally buoyant inside of the vat, and it has to use the scaffolding to hold the part up, but it's very, very sparse. So you get very, very limited waste with this kind of technology. It's extremely high precision. It's the highest precision 3D printing that you can get. And when I say this, I'm talking about production level 3D printers, not a Formlab or any other entry level 3D printers. Now we do have those printers in house, right? So I am a 3D systems reseller and partner, but I have to admit, if you're looking for quick and dirty, a Formlabs printer is actually good. Now, we don't use that to verify our parts before we go to manufacturing. Those are only used in very early preliminary design concept and development phase. When we're going to verify things before we go to manufacturing or functional testing, we steer clear of the consumer level 3D printers and we go for professional or production printers because we want to make sure we don't have a false negative or a false positive based off of an error that the 3D printer produced. We want to make sure that our parts are one-to-one when we actually go to manufacturing. Therefore, we invested in production and professional level printers to do that task for us. So to sum it up, SLA, you want to look at SLA if you want second to none accuracy, and also if you're doing relatively large parts that have big voids and you want to drop your costs in terms of producing those parts. The other thing is you have a much wider range of material properties from ABS, polypropylene, high temp, cast. So there's a wide range of applications an SLA system can actually provide to you. These are some examples just to kind of show the variety. So you notice on the bottom right an extremely small intricate cube. Top right, that's actually a one-to-one size engine block that was printed in the mode called quick cast, so you can actually get that and then actually cast that part after the fact. You have the top image to the left there that shows how clear this material can actually be made. Now that's not right off of the printer. I want to make sure that I make that clear. That's actually was sanded and then they put a clear coat on top of that. So don't expect it to come right off of the printer as is. It comes off of the printer like it looks in the bottom right if you get that clear material. You have to then buff it. And then right on the bottom, that's our Accura Extreme material. That's like ABS-like material. That stuff can make snap fits. It's extremely rigid. It's really good stuff and holds very high tight tolerances. Long story short is you have much more wide range of mechanical properties with SLA, and you can make more, or let's say larger parts more efficiently with an SLA system. Now, the limitations of it, you're no longer in an office-friendly type of environment, right? So multi-jet printing, I literally have one, actually I have two of them 3 feet away from me right now. I don't have to worry about fumes, I don't have to worry about mess, I don't have to worry about any of that stuff, special plumbing, nothing. Where with SLA, this is now an industrial piece of equipment, right? So this has to be out on the work floor, on the shop floor, special electricity requirements. It does have, the resin is an irritant, so you have to be careful with it. You have to have special disposal. So this is industrial equipment, right? So you're going to be putting this out not in the machine shop, because you don't want to put this next to a whole bunch of dirt and dust, but you definitely want to put it in its own isolated area, because it's not something you can just have on the third floor of an office building like the multi-jet printers, right? So that's another thing. The other thing is, or the last one is, it's now in a completely different price point as well. You're talking about production style printing. This stuff starts in the six figures, so you're not even going to humor getting one of these unless you have a six-figure budget to look at. That said, you can actually, this is stuff that you can outsource as well, right? This is the line of SLA printers that 3D Systems offers. Starting from the left is the ProJet 6000, then the 7000, which is just a slightly bigger version of it. Then you have the Pro X 800 and 950. Those things are massive, massive printers that you can print basically car dashboards on and hold the tolerance across the entire build of plus or minus 2 thousandths of an inch. So these are extremely, extremely precise and robust machines for production style applications. The other product that we used on this project was the capture scanner, right? So we don't only use the capture scanner for verification like we showed in this example with the Clever Cap. And with the Clever Cap, what we did was we got injection molded samples. We were having some issues with the assembly. It's kind of rough here, rough there, but that was fine. You expect that off your first samples. What made it so easy was the fact that we were able to actually just 3D scan the sample, get a report, and tell the manufacturer exactly where it is we need to modify and adjust. And then we were over those changes in a matter of a couple of days while they adjusted the mold and tried a couple samples to change the flow rate, the temperatures, things like that to check for warpage. And we were good to go. We didn't have to worry about missing certain parts that we didn't measure or not taking accurate measurements because of human error, etc. So the capture helped compress the timeline significantly. The other thing is we use this for reverse engineering quite a bit, right? So a lot of old industrial equipment out there starts to break down. They need replacement parts for equipment that doesn't exist anymore. The easiest way is just 3D scan the broken one and redesign it, or just 3D scan the industrial equipment that it's supposed to be on, where the points are, and you can design around that. So 3D scanning actually helps quite a bit in expediting reusing data that already exists in terms of physical hands-on data that you can just scan and get that into 3D, modify, tweak, and then fabricate using a 3D printer to verify before you take it to the machine shop and use up the gentleman's time to machine something over the course of a couple of days and also waste all that steel. So I will go at lightning speed through the rest of this to make sure that you at least see the rest of the 3D printers that are available via 3D Systems. We offer the full line of 3D printers, starting from FDM, which is fused deposition modeling. That's what you guys are probably used to seeing in terms of MakerBots and all these sub $1,000 or sub $5,000 printers. A lot of them, or the vast majority of them, are FDM, with the exception of some SLA printers like the Formlabs, etc. SLS is selective laser sintering. This type of printer you want to look at because it is tough. You can grab one of those parts, slam it against the wall, and it's not going to break. So you can get things like glass-filled nylon, things like that. SLA, we just went over. Direct metal printing is the future, I think, of 3D printing. We've gotten a lot of interest in this kind of application. You can do molds directly off of this with conformal cooling without having to go through the casting process. You can have just the end product be printed right off of the 3D printer for small applications like dental, or even big things like impellers, because the metal printers are actually starting to get relatively large nowadays. Multi-jet printing, which is off our 3600, that's how we created all the prototypes for the Clever Cap that you saw. And color jet printing, which is the one that you saw with the warpage in the earlier example. So let me just go through these. I noticed that I have 12 extra minutes. I was kind of leaving this as a if I had enough time. Seems like I do. So plastic jet printing, you can produce very rough models, low resolution. Where we've seen this be very, very useful is educational. They eat this up. They're low-cost prototyping, and actually low-resolution jigs and fixtures are good for this. They're relatively robust little parts. They're inexpensive to print, so it's a good thing to get. How does this work? Well, it's basically just two filaments that get melted. It's a high-precision hot glue gun, essentially. That's what it is. So we call it polyjet printing. The industry calls it fused deposition modeling. So PJP and FDM are basically interchangeable. Bad thing about this is you need to actually break off all this material. So prints, and then you have quite a bit of manual labor they have to go through to remove the supports. This is an example of it. So you'll notice that it has a low entry level, very inexpensive to start to get used to 3D printing. We offer the cube for this, and also rigid prototypes, but limited on geometry. The accuracy and tolerance is an issue. And also if you're getting into printing multiple parts, the speed starts to get very slow, and there's a learning curve on how you should orient these parts. You can run into a lot of issues in getting good quality parts off of these printers because it's kind of tough to cater your design to the limited printing capabilities. But this is our Cube Pro. That's essentially what you can get from that. Now, SLS, this is, I consider, one of the coolest 3D printers because it can actually produce end products, right? So New Balance uses it for the soles of their 3D printed shoe line. This Italian company is using it for eyeglasses. You can actually use it for drones. They have very large build volumes, and they're very, very robust parts. So end-use parts that you don't have to worry about breaking once you put them in the hands of your customer. SLS printing is good for that. How does this work? Vat of powder that then gets solidified with a laser. So a laser actually goes in there and sinters the powder together. There's a variety of different materials from flexible to rigid, high temp, etc. So it's a good printer for really robust stuff. The other thing is you can print very large parts very inexpensively on here because all of that support material is reusable. You do have to put in a certain amount of virgin material every time you run a print, but in contrast to multi-jet printing and what our competitors offer, which is polyjet printing, which are expensive once you start getting into large volume parts, SLS and SLA, large volume parts of the support material gets sucked right back into the machine, and you can have relatively inexpensive production parts or short run production off of these printers. Other thing that I wanted to mention real quick, some people are using this for bridge manufacturing. While their tools are still being made, they can actually do some short run manufacturing of their part in a 3D printer while the mold is being made. Some of the parts actually on production 3D printers via 3D systems are 3D printed right off of an SLS machine or an SLA machine. So even them, knowing that they only sell X amount of large production printers per year, might not justify a mold that can make 100,000 units. Let's just 3D print them because we have relatively low volume for those. So they use it in-house as well. So why would you use SLS? Very durable, high throughput, affordable price point for making actual physical parts. So you can actually offer end-use parts off of these without breaking the bank. Limit, well, it's an industrial machine, right? It's not office friendly again. So you're talking about you have to have this in its own area. There's dust. You need dedicated staff for it. You need nitrogen tanks. So it's an elaborate piece of machinery built to last. I know there's some out on the market over 10 years old and they're still kicking. Limitation, fine details, right? So you don't want to go to this one for very, very intricate fine details. You leave that to MJP or SLA. With SLS, you're talking about, rough kind of detail. You're not going to be able to get that fine print or the extremely sharp corners, but it does hold the tolerances very well, better than FDM or CJP, but it doesn't hold up to SLA or MJP, just to keep that clear. These are the SLS systems offered by 3D Systems. The Pro X 800 and the S Pros, depends what materials you want to run and what size you want to do, but we offer all those as well. Then direct metal printing, which I think is the future of 3D printing. I know a lot of our customers are very excited about it. Works just like an SLS system, except for instead of having powdered nylon and glass-filled nylon or polyamide, whatever it might be, this actually gets filled with titanium, stainless steel, cobalt chrome, copper, aluminum, steel, stainless steel, things like that. So you can actually produce metal parts directly off of a printer nowadays. They're better quality than cast parts because they're actually 99.9% dense, and you can actually produce parts of biocompatible material like cobalt chrome and stainless. So something that you might want to look into if you're in the medical industry or aerospace or heavy industry kind of things. These are some examples of it. The other good thing is it comes with a really cool software that allows you to do that kind of porous design that you see there on the hip implant that you see on the right. That was not CAD'd by hand. I know everybody on this webinar knows how to use CAD. I can just me personally, imagining how to design that lattice structure would be a nightmare. So luckily there's a software that automatically generates that lattice structure. So the good thing is softwares are actually starting to cater to the 3D printing software, capabilities. You'll notice that, Autodesk now has, buttons, shoot to 3D printer. They're even starting to get into 3D printing check software, so you can actually check whether or not it's 3D printable or not based on the 3D printer that you choose. So 3D printing is starting to get integrated into your life, whether you like it or not. I say embrace it. It's actually very good technology. As soon as you start using it, you're going to find a lot of applications for it. I know a lot of the times people go and they say, oh, the technology is cool, but I just don't know exactly where to use it. Believe me, try it, test it out. If anything, buy an entry-level 3D printer. Get used to it, see what its limitations are, and you'll start opening up your eyes to, oh, wow, if this printer was a little bit more accurate, or if I had the material that I needed, I'd be able to use it for X, Y, and Z, right? So by no means am I saying go out there and buy $1 million metal printer, though I'd love to sell it to you, but just know that 3D printing is here. It's here to help. It helps us significantly. So take advantage of it. It's definitely something that helps out a lot. If you're a machinist, don't worry, your job's still intact. There's things 3D printers cannot accomplish and can't accomplish nearly as efficiently as a machinist does sometimes. But a lot of the times, I'm sure you're running parts that aren't working, don't work, and it wastes your time. A lot of the times, people can just run it on a 3D printer until they're ready for you and then send it out to you, and you can use your time more efficiently. Color jet printing, I'll be quick because I know I'm starting to run out of time at this point. Color jet printing we use a lot for just aesthetic mock-ups, right? We don't use it for engineering type applications. Reason being is because they're not the most precise printers, but they make extremely pretty parts. If you want to make selfies, we have some companies that have purchased these printers solely for a 3D selfie kind of business model. Architectural purchases these quite a bit to do scale models of their buildings with very high level of detail. And then also consumer products are a big hit as well because they can actually hand somebody a full color model without any added type of work or effort into it. Us personally in-house for engineering applications, we don't use color printing. The only time we actually use color printing is for small marketing demos, things like that. Good thing about these printers, very inexpensive to run. All of the material is recyclable, just like on the other printers, SLS and SLA. So you can actually run these parts, and it's not going to break the bank. So this is one of the things that prints very fast, very intricate in terms of colors. The precision in terms of geometry is hit or miss, right? I'm not saying that they're bad printers, but for engineering applications, I would not recommend looking at this one. I would recommend looking at a multi-jet or an SLA or an SLS because color jet has its limitations in terms of accuracy and tolerances, but very, very pretty colored parts, right? So if you wanted to make relatively bulky, thick geometry parts that don't have to hold extremely tight tolerances, go for it. These things are very, very nice printers. The nice thing is cheap to run. Bad part is post-processing is kind of laborious, right? So you do have to kind of excavate these parts out of a powder and then infiltrate them after the fact. This is the full line. Essentially what you're looking at from left to right is build size and color quality starts to build as you start going to the right. So let me just summarize what we spoke about here today. I know it's been a long 1 hour, and I appreciate everybody showing up and taking time out of your day, especially in the holiday season. I know everybody's starting to disconnect little by little, but long story short is WB Engineering product development company. We help customers equip their teams with high-tech 3D printing and scanning as well as training. We also train on how to effectively optimize and refine your designs, specifically in injection molding plastic applications. We do offer the full line of 3D systems printers. If you want a demo, we can go up to your office, meet with your team, show you some demo parts. We can even print out a benchmark part for you if you have any questions or doubts about the technology to see if it fits your need. Feel free, email us at sales@wb-3d.com. We'll be more than happy to talk to you, see if it's something that might or might not work for your application, answer any questions that you might have. And same thing goes for the 3D scanner. If it's something that you might be looking into, we use a 3D scanner here almost on a daily basis to help verify a lot of the things that we design and go to manufacturing with. So these tools have made us a lot more effective and efficient. I can tell you firsthand that with the little staff that we have here, we do what I've seen companies do with 2 or 3-fold the amount of staff. So you probably already have a good team in-house. If you're getting overrun with a lot of work, make sure that you invest in the technology for your team to use, because your team already knows what's happening. Hiring a whole new set of people or more people sometimes isn't the most efficient way to do it. Just superpowering the people that you already have, already know your workflow, already know the ins and outs of your products. That's the way to go. We've done it in-house. We've kept our overhead costs low, and we've been able to win on contracts bidding against large Silicon Valley type companies because we are able to make 10 and 20 mistakes before the time that anybody's able to even notice that we've made them. 3D printing allows us to design, develop, and optimize our products over and over and over again in-house without overrunning our budgets and overrunning our timelines, right? So, we can easily 3D print something, get it off the printer the next day. It costs $20 in terms of material, and in terms of labor time and cost, maybe only 10 minutes of somebody's time to post-process the parts, because they just have to take it from the printer to the oven. So long story short is, seriously look into 3D printing if you guys are designing and developing products. It helped us out significantly. It's really one of the main reasons why we still exist today. We've been around since 2007. We started shortly after the recession, and we were able to survive due to the fact that we had technology that put us out in front of everybody else. So thank you very much again for your time. Again, feel free to give us a call. My name is Warner Blumenthal, and have a good day. Take care.